Anybody still to do that or all? You are finished? Raise your hand. Now you can use the slip, green, red. If it is not done, red one. You are putting both. Right? We have either one. Green means done. Yeah. Pink is not done yet. Yeah, those who successfully done it, you put the green one. So that. Okay. You are connected to Wi-Fi?
Yes, sir. Sir, some problem happened. Sir has seen that.
Okay.
That's only I am trying to.
Maybe that lane some problem. Oops.
Yes. Vinod, खाली है ना? उठा दी.
Shiaram, your color is neither green nor pink. What do you mean by that? Pardon?
Sir, only one was left.
Okay. Okay.
नहीं लेना
Then sir said that in my laptop some problem is there and I can't do it. So after months I am trying to again. I'm doing N. Before that I have done A. This time I have done N.
Okay, well,
This time again not.
so let's do something. So because yeah, it's gonna take a while, I think. So what you can do is you can.
Metagenome state is now. Other packages are down. Only one is my Canada.
Yeah, but I think it's gonna take a while. We'll see. It's ready for when we start, and for the meantime, maybe you can join her. Yeah. It's the only way. I mean, we cannot speed up. So it's installing. It's coming. Almost there.
Sir, shall I stick it or I will go? I will stick this or I
Yeah.
will.
Who else is missing the sticky notes? And oh, you have the pink. You don't.
ना मुझे भी एक ग्रीन फ्यूचर में मतलब फुल
Okay, shall we start? Okay, maybe there's one thing here. Yeah. Otherwise, I'm seeing all okay. Another one here.
Okay, so yeah, I know that there are still some red flags,
One or two only.
one or two. So some of them are some incompatibilities and well, other things that will take a bit longer to solve. So my proposition would be that the person that has something wrong join to the network and do it together. Yeah, because that one, for example, it's more downloading packages. Then, well, Guillermo is gonna start his presentation. So,
Can you speak a bit louder?
yeah, so where I can come. Yeah.
And just one more thing. So if you have the sticky note, the pink one, and I go there and we solve the problem, hopefully, then please remember to take it down because otherwise 1 minute later I will be again there, right? So please be mindful of that. Thanks.
Okay, well, then, Guillermo is connecting to internet. So in a moment he will be there, I think. So in the meantime, I think you can start downloading the Amplicon Practical, right?
Yeah, well, I have been there presentation.
Yeah.
No, but it's honest. You need to download from yes. So if you go to the Google Drive, there is one you don't have to download everything from that folder because the folder that is available there is tags and data are big and there are examples. I just add them for when you need to run your analysis. So you really need to download the whole folder except data and tags folders. Yeah.
So we are going to solve the problem of the internet connection, and then we will come back to it. So is there any way to connect to the internet?
The internet is also disconnected.
Okay, so we are ready for some hardcore bioinformatics. So, well, we have some issues with the packages, but almost all of you are there. The ones that had a problem, please don't worry. You're going to still get most of the practical and run most of the things. Just if something's not run, just look with the one next to you. Okay? So first, what we need for today. In the Google Drive, we have this the folder called Amplicon Day 2. So you just need to download the ones that are in a square. So the folder workspace, the metadata.txt, the amplicon.rmd, which is the R code, and well, the PowerPoint if you want to have the slides. So please download it. If you download it already, good, but at least that you download it this morning, the earliest, because I did some little change yesterday. So please do download it again if you download it like before this morning. Okay, what we do next? We go to, you get the download, everything that you download, you create a folder in your desktop, you call it as you want. In my case, I call it Amplicon Try, for example, and then you just paste everything that you download in that folder. So now we wait a moment, and please keep this. If you have any problem downloading, Luisa is there, Victor is there, we have the stick notes, let's use them. It may take a bit to download, but it's just 50 megabytes, I think, everything together. So I will put this one back so you know what to download.
Yeah, so the ones that have the green one up now is because they already downloaded?
Or because you had it already there.
I see already a red one. Okay, it's downloaded.
Okay, so in every step, I would say you put the stickers down, and then at one moment I will say, okay, the moment of truth comes, and then you put the green or the red one. Okay, please? So then you don't have, or you forget that you put the green on your laptop.
So everybody did it already? Downloaded, created the folder? Yeah?
Everyone good? Please raise your hand if you have a question, and Luisa or Victor will help you.
Yeah, no, I think it's all okay because there is no red so go on, Guillermo.
Okay, so all of you now should have a folder in your desktop or whatever you want, but in the desktop where you have all these files, right? So now what you do is like you need to open the file amplicon.rmd with R.
So you click with the right.
You click with the right button, right click, you choose open with RStudio. Okay? So if everyone has a problem, read the stick note. Descargar esos 50 megas. Sobre todo es el workspace con todas las variables ya hechas.
Okay, is everyone good? Okay, please raise your hand or put the red post-it if you, the red stick note if you have a problem. No? Well, or not. Okay, so we're gonna move on. Now you need to see like something like this. You have your R. So now remember from yesterday that you could go to a session, set working directory, or choose a working directory, and then you need to choose the folder where you have all these files. Okay? So please do that and raise your hand if you have any issue. ¿Mm? ¿Eh? Sí. No, sí, sí, sí.
So remember that it was in session
Mhm.
set as working directory. I think you can continue.
Everyone good? Okay. So we're gonna continue. So well, this is about the packages, but we did with everything before. So we're gonna start a bit with the practical now, and the practical of today. We're gonna talk first about some of read quality and inspection, and then we're gonna move to the Amplicon 16S Amplicon data analysis. This practical is organized, so I have slides where I have all the plots that are generated in R, and then I have some little comments that maybe say code lines and 2 numbers. So then when you see that, you still don't run it. First, I will explain it, and then you listen to me, and we're going to interpret the plots together. And then when I finish, I will tell you, okay, now you run the line. So then you get that lines, and remember from yesterday, you have that green play icon in some chunks of code. So you just need to click that one, and the magic will happen. But first, let me come back. In all the files, you see that in R, you have the folder, well, in the bottom right, you have like a folder called workspace, right? So do click in that folder, and then you will see a file inside called end data. So please remember, go to the open the work dataset folder from R. So you just do click in when you see workspace, and there is another file inside, and you need to click the name of that file, and then a lot of things will come up in your upper right side. So you have the workspace, you click it, and then inside there will be another file called env.rdata, and then you click on that one. I will do it with you, that I see that there's problems. Okay, so you see that I have like something similar to you. I have this folder workspace. I click it, and then you have this file, right? Do you see it? And then when you click that file, it tells you this, and then you say yes. You wait a bit, and it will load all the tables and everything that we already pre-compute. So you will see a lot of variables and tables that will appear in the upper right.
So basically, this file contains all the information needed for this practical.
Exactly.
Okay, so here also you uploaded all the libraries and all the programs that we have to install today. Yeah?
No, that doesn't load it. They need to run that chunk of code. Okay? Does everyone see this with variables and things inside? Can everyone have that? Yes? Okay. So now we need to load, please. If everyone is good with that step, if not, please raise your hand or put the red sticker. Victor.
Yeah, good.
Luisa? In there? And there? Well, okay. Are you okay here? Ah, okay.
This data, we didn't download this before from Workspace. No, it's downloaded.
Yeah, that's what I said. Like maybe you download it before or something, and I
We
update.
didn't download from Workspace. We don't know we had to download this also.
Yeah. So just upload it,
5
put the
minutes.
folder. Don't worry. Yeah. Yeah, you're good. You see that? My file setup could not be for now. We are. But then file graph test. But why you trying to load this package?
It is there, sir.
Yeah, but we don't need this package. We need filosec only, not
Only
filosec,
filosec.
no filosec graph test. But don't worry. Now you see that it's a library there. Now you are gonna run that code. So open the RMD. Or go to files. Files. You need to open this amplicon RMD. Then here. Now stay there, okay? Just stay there. You're good. Just stay there. You have everything loaded, and that's the code that we are gonna be using, okay? Okay?
I think it's okay.
Everyone good? Okay, so now you can see you need to open the amplicon.rmd. You have to see it here, and then you need to go to line number 24, and then press the play button. So that will load all the packages that we were installing. Okay? So now is the moment of truth. Remember, warnings are okay, errors not. All good. Dime.
They are downloading the Amplicon data.
Yeah, so yeah.
Which file should we copy now?
You can copy the workspace,
Workspace.
that one, and you just, you create a folder in your desktop
I have
and just copy everything in that folder. Just copy everything.
so just take this.
No. Go back, go one up. In this, yeah. To double click there, where you did. Okay, you need to go. Yeah, okay. All of that, just copy it. Copy
Everything.
everything. Just copy it in a.
Okay, I have some already. I have Amplicon. I have Amplicon Practical.
Okay, I just everything maybe except tax and data. So everything except tax and data because that ones we're not gonna use it.
The workspace. Then you need to open HTML. Workspace and HTML.
Yeah, no, that one. Wait, yes.
What is missing here?
The workspace table. Okay, look. You see your workspace table was downloaded compressed as zip. So decompress it. So go to the folder and zip it, yeah. No, you need it like the uncompressed. So it needs to be a folder, not a .zip. Yeah, extract it. Okay,
HTML report.
you can do that one too. But okay, now you have your R, so go to R.
It's a program.
Open the R Studio. And now you go to the folder. You see that sometimes you need to go again. So you go to workspace, and then you click full R data. Then you say we download everything except the tax and the data folders because that ones are. Okay, now you wait and you see that it's still doing something because it's a stop sign. And then when it loaded, you have here a lot of things.
Okay. And the first one we have opened also, so that we have to document the workspace here.
But when did you download this, all this data? Right, just now?
This one? Yes, I think this one.
Because I think you may have the old version. But I think for now it's okay. But you see, now you have a lot of things, variables, okay? Everyone good here? Mhm. Uh, that one, yeah. Just stay there. You have it everything loaded. You're good. Okay. Yes.
Actually, I don't install Filos in the phone. When I'm going, like,
You have the same problem. You have the
but
quote.
it's not
But yeah, but
responding.
first you see that you have the quote thing. You have it wrong written. It's like this. This means that you didn't copy good, so you are missing a bracket somewhere. So let's try to do this. Okay, but this one could take a long time to install.
It will take long time.
So the ones this will be installed. Let's see, maybe it doesn't take that much for you, but that's why we did the installation before for
I
everything.
thought that Filos graph test and Filos
Yeah, you had the wrong one. But it's okay. Just maybe you have to wait a bit, but if not, follow it in someone else. And anywhere, I'm gonna have all the plots in the thing, so everything is gonna be there. Yeah. One moment.
Sir, update all some.
Always, you have this. Just
Sir,
write.
sir, if we will do it, will take more time, sir. It's taking very long time.
Yeah,
And
that's why we had to install it before.
Sir, shall I do
But
it?
you need to install. I mean, we can try to with n, but with n there is high chances. So now, first you are in the okay. I'm gonna repeat it.
Yeah, but I'm working on it. I was gonna ask you.
Okay, okay.
¿Qué hiciste tú con la persona que no podía instalar en su propio path? En el sticky note le pasa eso también.
¿Cuál? Que no puede instalar eso?
Unwritable directory.
Como que no hay permissions. No hemos podido resolverlo. Eso no se puede hacer nada. Es que yo ahí no sé de cómo dar permisos. No sé quién en su ordenador no tiene permisos ni nada. Ya.
This Filosec got downloaded, sir. Now, ma'am.
Try library filosec.
Sir, Filosec downloaded.
Hmm?
Filosec downloaded.
Ah, then you're good.
Sir, data 2, data 2. Ma'am
You don't
said,
have data
she-
2?
Ma'am said that she has some alternative because that
Search for data 2 here.
It's not there, sir. Ma'am said she
Okay.
has some
So
alternative.
try to install data 2, but you need to install it with how we have it in the guideline. Okay? So we have the guideline. Don't try to install it in any other way.
Sir, like I have tried this alternative. Is there that also I tried?
Like
It is
try this one. But do you install DevTools?
Yes, sir. Yes.
Okay, so then copy that 2 lines and paste them.
Sir, here also some problem happened. Just now, ma'am had checked.
Enter. Okay, you didn't have our tools. So now it's gonna say yes, and it needs to be installed something, but this is gonna take some time. This should be done before.
It is done, sir.
Okay, good. So this will take some time, if not in the meantime, but it's okay. I have all the plots in the screen, so it shouldn't be. You can still follow everything. Yeah, there's some permissions issues.
Okay, let's continue.
Okay, just that I saw that some of you don't have it. Where you download, you need to open the amplicon.rmd and have that file here. No other one, just that file. So you click in amplicon.rmd to have the code here, okay? Good. Okay, everyone good? Okay, first that I said before, don't worry if for some case you cannot install it or if it doesn't run. I mean, we don't have to run that many things in this practical. We just uploaded this everything. I will show you the plots and then you're gonna try to run it so you see it in your computer. But if you cannot run it, you're not gonna miss absolutely nothing, okay? So don't worry because you will still get the 100% of the whole practical, okay? Okay, so we move on. So we are in the practical now. So first, we're gonna check read quality, we're gonna check read inspection, and we are gonna do also the full 16S amplicon data analysis. So everyone here, I guess everyone knows what is a read from when you send to sequencing. So then we start with our magic slide that we have the whole course in this slide. So which parts are we focusing in this practical? So you yesterday isolate some DNA. Kumar, that is really efficient, sent it already to the sequencer. And we got our reads back, okay? So they send you, so we are in this step. So what we sent to read? As this is on a slide from Victor, what is the 16S gene. So we send to sequence the B3 and the B4, that as you remember, is two variable regions from the 16S gene. So that's the section that we are sequencing, okay? So we use primers to get reads from that region, from the 16S gene. So now, okay, we send it to sequence, and then what we get back? We get a file format that is called .fastq, okay? So you will say like, oh, this sounds like a FASTA file, that maybe you know what is a FASTA, but it's not a FASTA file. So what is a .fastq format and how it looks? So this is an example of one read of that file. So if you open that file, you will find a lot of this. So 4 lines is one read. Here, if you see more than 4 lines, but because the second and the third one is the same line, and the 5th and the 6th is the same line. So what all these lines mean? First line, we have the ID of that read. So then every read of your file will have a different ID here. Then, next one, we have the sequence itself. So this is the sequence of the read, all this. Then, next line, we have a separator. That normally is a plus. And then the next line, we have the quality scores. So you see that here, quality scores, we see a lot of Fs, and we see like this hashtag. So what this hashtag means? Well, if you look at the sequence, we have an N here. But I don't remember any nucleotide that is called N, right? Maybe we are wrong, but I don't think so. So when you see an N in the DNA, an N means that the sequencer machine couldn't identify the nucleotide of that position. That's why in all of them we have an F, that means kind of good quality, but in the second one, where is the N, we have a hashtag. A hashtag means that the sequencer didn't work good there and that position has a really, really low quality. So at the end, when you have a file like this, you have like thousands, sometimes millions of reads. So you have like these 4 lines for each read. So you're not gonna go read by read in millions of reads to check them. That's impossible. So sometimes you need to use other software that compile this, that we will see later. But then we see the quality score. So yeah, for me, you show me an F, okay, and I told you the hashtag, but what this F means. Well, here I put like a link. In this link, well, this is a checkpoint, everything good here, understanding? You go to this website. So in this website, it tells you a bit description of what these letters means, the qualities score. So you can understand that first you have a lot of like random symbols. For example, you have your hashtag here, and all of them, this is the quality score, have like really low quality score. What could be a good quality score? For in genomics, bioinformatics, good quality score is when it's above 30. You can get that rule. If it's above 30, it's a good quality score. So you can see that first we have all these symbols, and they go from 0 quality score to 14 quality score. That is really bad. Then you have numbers, 0 to 9. And the quality scores are until 24. So it's still bad. We are getting close to 30, but it's still bad. Then we have also another batch of symbols. That now we arrived to the 30. So these ones would be okay, not ideal, but it's okay. And then we have the letters. So then if you see letters, you know that the quality is pretty good. So that's a rule. But always, I never remember this by heart, it's impossible. So then you have the link, you can always check it. But it's what I said. You are not gonna go read by read, checking all the letters, because then your PhD will end and you will have nothing. So you need to summarize everything, and there are softwares for that. So now we are gonna move a bit to the 16S workflow, and we will check the quality also, what I said. But first, we're gonna use a data set that is based in some experimental design. So in this experiment that we did, we have first soil, and then we put a tomato plant in the soil. So we were growing the tomato plant, and when the tomato plant was in the spermosphere stage, we took we have 4 tomatoes, have replicates. We took 4 samples of the spermosphere stage. Then we let it grow, and then we have the rhizosphere stage. And we took another 4 replicates. And also, as control, we took bulk soil, so just soil. So then we sent, as you did yesterday, we isolate the DNA. We give the DNA to Victor. Victor is also really efficient, so he sent immediately to the seq sequencer. So then we have a total of how many samples? 4 plus 4 plus 4. So we have 12 samples in total, okay? We have 2 conditions, spermosphere, rhizosphere. Well, 3, and the third condition, that is more the control, that is just soil without plant. So we want to compare this. We can see, using the 16S. Well, with 16S, what we do? Taxonomic profiling, right? We want to know the taxonomy. So we want to know the taxonomy of the bacteria that is just in the soil, that is in the spermosphere, and the rhizosphere, and then compare to see what's happening there. So first, what are we using as taxonomic unit? In this case, we are using ASVs. So this slide is from Victor. You already know a bit of ASV, and you had a lot of questions, I see. So I think that's good that you got it. So basically, with ASV database, we don't put a % cutoff and anything, and we got some units that we call it ASV. So we are using the ASV as our taxonomic unit in this analysis. So this is the whole workflow. It's big, don't get scared, but we can see that there are 2 main parts. The first part, or objective, is generate an ASV table. You remember what was an ASV table? So we have the ASVs, and then the samples, how many reads of each ASV or taxonomic unit are in each samples. And there are different steps. We will go through the most important ones, because there are way more, but we're gonna just see the most important ones, because this is a complex workflow. Then you get your ASV table. Okay, Now what I do with my ASV table, because it's super big. You can perform a statistical analysis and make nice plots to put in your PhD paper. Okay, so we're gonna start first with the first part, how we generate the ASV table. So what did we have as input from the sequencer? Anyone remember the name of the format, or everyone forgot it already? Good, the .fastq, that is the reads. So first, we need to check the quality. And with 16S, normally we are doing forward and reverse, right? You understand what is per end reads, forward and reverse? So then we need them to overlap, because if we have them overlapping, then we can get a consensus read that is longer. So you are just merging two reads into one long read that will cover the whole region that we sequence. So this is quality plots. So what is quality plots? We have one for the forward reads, and one for the reverse reads. So basically, this is summarizing all that letters, that Fs, and all that quality things that we saw. So in the x-axis, we have the length of the read. So we see that they are like 300, around 300 nucleotides long. And then in the y-axis, we have the quality score. So I told you before there was a quality score that you can use that is above is good. Which one was it? Anyone remember? 30, good. So then we are checking, and we see that this is really common when you're seeing reads, that at the beginning, the sequencer is reading really good. So you have a really high, almost perfect. Perfect would be 40. So you have an almost perfect quality score. But then when the sequencer is still reading, is getting tired, let's say, so then it starts to go down. And then with the reverse, it happened even earlier. So with the reverse, the sequencer gets more tired, let's say. So we need to check this, because sometimes you see that at the end, it drops, you have this drop, and you have really bad quality. So sometimes you want to cut them and just have like the good quality part, right? So in this plot, I draw a line in the 30, because it's the one that we consider above is good. And then I decide that, okay, for the forward, I decide 275. So I will cut it there. And then in the reverse, I decide that because it was a bit earlier, 210. But hey, this is the most important step, because you need to be really careful, because if you cut them too much, they won't overlap. And if they don't overlap, you cannot merge them. So you cannot get the whole region. So you cannot cut too much. So this is, well, yes. So this is after we filter. You see, we already cut them. Now here is 200 instead of 300. So you can see that they are shorter. We cut them, and now they look like nice quality, right? They don't look that bad as this one, at least the end. So we have this. So then we merge them. So here you can see different steps of the data too, but we have all the reads at the beginning and the different samples. So we have all the reads. You see that we have that is variable, this number. In some sample we have 80,000. In other ones we have over 100,000. Then there are different steps that we are not going to talk that much in detail, but then we see that we merge. This is the moment that we merge them. So we see that we have good numbers. We went, for example, in the first sample, okay, we went from 80,000, and when we merged to 43,000. That's okay, that's good, we have 1,000. But then what happened if we trim the reads more strict? This is the trimming that we apply, so in the forward. So we applied at 275, but some people could say, hey, but here, you're still here, maybe it would be better here. So I was like, okay, let's try it. We put it at 250, so it got good. So it gets cut at 250. Now what happened? You get this table of the steps, and when you go to the merge column, you see that the numbers are really, really, really low. So that you cannot do anything with that. So that's the thing. You need to look always for scores above 30, but you need to be flexible because you cannot cut them too much because if not, they won't merge. And then you cannot get the long read that is what you want. That is the long read of all the region that you wanted to sequence. Okay, so this is a really important step to do always when you get reads, because sometimes you trust the company, the sequencing company. They have these super expensive machines, but they are not perfect. So if you see, for example, that your read start here and start to drop here, you need to call the company and tell them, hey, what happened? Like, or you repeat it, or I won't send it to you anymore, because I paid that money for this. So it's important that you always check it. So, okay, we have our reads, we check the quality, we know the format, we saw that we cannot trim it too much, that we need to be flexible between the quality and the length. So then we run this through data2 to generate the ASB table. So if in your R code, well, first I will explain the ASB table. Victor already explained. You have as rows the different samples, and as columns you have all the different ASBs. I didn't get into detail of how the data2, but you can always read the paper of how, but Victor explained a bit of how these ASBs are calculated and everything. So someone tell me something weird about this table. I heard there some more people. What would you say? What get your attention of this table? The zeros. There is too many zeros, right? So what would you think if you see that many zeros? That is wrong. Well, no. We are working with compositional data. So in compositional data, one characteristic of compositional data is that most of always when you're doing amplicon analysis, most of your table is going to be zeros. Maybe sometimes even 80–90% of the table could be zeros. But that's okay. But it's something to take into account when you are applying statistics and models that we will see later. So now, if you are in your R programming, if you run this line, ASB table equals data frame, brackets, OTU table, piece, it will generate a data frame. Remember from Luisa's practical yesterday, a data frame. So try to run that line, and then the ASB table data frame should appear in your app right, and then click it and open it in your screen. So let's try, if you can manage to do it. No, it's not a line. This one, they have to write it. And if everyone has a problem, write the stick note. No, en el R. So this, you write it in the command, in the console, okay? In the left bottom. That line. Try to write it.
So you have to write this command, okay?
This one.
The one in black. You have to write it exactly like it is, eh? Yeah. So you need to go to the command line, yeah, to the console.
Okay,
and
yes.
then write this command.
Write that line and enter.
And then enter.
Yes? Okay. So I'm gonna do it now, so maybe you can see. So you see, here, I wrote it It's still thinking, and now it's finished. And then it should show up here, ASB table. It should show up here. Can you read it good here, or is too down with the table you cannot read it? Okay. If anyone has any problem, let me know, and Luisa, and I can go help you. Yeah. And also use the red, please. Okay. Now you're going to find a function. Okay, did you load the phylosec? Because this is a function of the phylosec. Now it's working. So it's that you didn't have load the software. Yes? One more.
I want to.
Oh, okay. Look, see. You put that. You see that you have that. Before OTU, you have the thing. Remove that.
I want to remove
Okay. Yeah. Sometimes with the plus, because this is expecting you to write more. So when you have something like this, if you press escape, it will come again. So, and here, if you don't want to repeat it, you press arrow up, you have it back. And then now you can change it now. Exactly. And then you can edit that. And then now you
Put your cursor here. And then now enter.
Now enter. And it's working. And then it will appear that variable there.
to copy or what to copy it like you copy where do you press?
Like always when you finish something, when I finish I will tell you, but always when you finish some command, you press the up arrow, you will get the previous command that you ran. And so you press it 2 times, you will get 2 commands before. So that's really nice because sometimes you want to run something again. Or like this, it didn't work, so you just want to do the same but change something and it will run.
Upper command. But now it's still running.
It's still running, yeah. Yeah. But you didn't have the phylosec package. Yeah. Yeah, the problem is like you didn't have this. So try. I mean, you will have to install also this package. So do install.package and copy this info dbb data.
Sir, can I get here the package?
No, you need to write it here. So you need to write install. Let me do it for you. So here. Packages, and then just copy the genome info with the quotes. Copy with the quotes, put it there, and enter.
So that,
With the quotes, you copy that one, perfect. And enter. Okay. The problem is you get a weird quotes. So these are not the quotes that we should get, because sometimes when you copy, there is some weird quotes, okay? So now,
so then again I have to, after installing this one, again I have to copy this ASB.
and then you do the library phylosec again.
Okay.
And if maybe it works, or maybe you get into another issue, like we will see. Everyone good here? Okay, look, now it's installed. So
ASB, that one.
So let's see if now your library phylosec loads. Weird. You couldn't notice it's getting. I think it's me getting close to the camera. Yeah, it's the same issue that you were having before. I'm sorry, but if not, you can see it with your list. Or, I mean, it's the table that we have there, so don't worry. It's like you have some permissions in your laptop that I don't know how you, in your own laptop, you don't have a permission. So that's something to check.
Change your laptop. Give it to me, this one, I'll use it.
Okay, everyone good? Okay, so now you have, please listen here, if you manage. You have the variable here, ASB table. So click on it. And you will see it like here. Okay, so who can tell me, opening the table, how many ASBs we have? Hmm? Good, I hear people saying. Here, you can see the description of the table. So you can see it's telling you you have 12 entries and 6,850 columns. You can also see it here. It's telling you 12 observations. So observations are the rows of 6,850 variables. So the variables are the columns. So here you can explore, and that's like the amazing thing about RStudio, that you can open all these tables, and then you can explore them like interactively with other programming languages. That's not that easy. And then you can go. So then we are gonna try to generate the total number of counts of each ASB. So how much are in total of each ASB in all samples together? Okay? So for that, you can follow me. We are gonna say total number, the equal thing that is like that, the arrow, and then this is a data frame, right? Yes. We are gonna do row sums, call sums, and the name of our table. Okay? Boom. We run it, right? So you run total number, the arrow, call sums with the first S in capital letters, brackets, and the name of your table. And then enter. You write it and enter. And you know that you ran it because then it should appear here at some point, total number. You good? See? Total number. Okay. Yeah, but it's run good that you see it. But then if you scroll here down, okay, then scroll up, you can find it. If not, okay, I will do that now. Here for everyone. Okay, some people, you run it, but please listen to me. You need to understand. Yeah, sorry. Okay, okay. Luisa, there? Good there? Let me see. Yes? Yeah. You get it. You didn't get an error. You see, when you run something and it doesn't say anything and you just show another error, it worked. It worked good. So you see the thing that I will explain it now. I will resolve your answer, your question. Don't worry. Vic, Víctor, ya todos están hechos. Ya, esto es que no le funciona nada. Que no, es que le da el engine, eso no funciona, Víctor. Okay. Luisa? Good. Okay. Okay, now a lot of people are asking me, I run this, but then, okay, what happened here? I just run this line, it say nothing, and I got another arrow. What happened? So to understand the line, we remember from Luisa from yesterday that sometimes you can create a variable, let's say. So here, we want a variable that is called total number. We give it that name. So we put total number, the arrow is like an equal. So we are saying total number equal call sums ASB table. So then if we want to see that number, you can just type total number and enter. Yeah. So, okay, so to see that you have like the variable, you store that count that we calculated in a variable called total number. So if you write total number and you press enter, it will print that variable in the console. Okay? But you say like, okay, that variable is too big because we had almost 7,000 values, 7,000 columns, sorry, that is 7,000 ASBs. So then we're not gonna check like all of them. So now we're gonna try to get this table and put it somehow in the table. So for that, sometimes it happens to me, yes? Sorry? I can't hear you good. The step before. Okay. So here, you see it say total number equals colsum's ASB table. And a lot of you were asking me, okay, but we press enter and then a new arrow appeared, so what happened here? What we did is store that sum that we wanted to do it in a variable called total number. So then if you want to see the inside of that variable, you can just write total number, press enter, and it will print it, right? So then, but printing like that in the console is really annoying. So sometimes, here my boss Victor tells me, hey, I want the ASBs as rows and the samples as columns because I don't like it like this. How we do this? For that, we are going to write the following. We are going to write this ASB table, that is our table that we already have, equals or arrow. You can always put arrow or equal. So if it's easy for you, you can just put an equal. T brackets ASB table again. Okay? And now we press enter. And boom, magic. Now we have the samples as columns and the ASBs as rows. Okay, so everyone good here? Okay, so now you see, like, you remember the format and data structure was data frames that we were using it. So sometimes, always that you use this T function, that it means the transverse, it changed the format from data frame, to a format called matrix. How can you know the format of a table or any variable that you have? You can just type the following. Type of, altogether, brackets, ASB table. And here, it doesn't say data frame. So it's not a data frame. So it changed to a matrix. So this is some basic operations that I wanted to show you of data manipulation. One of the most important ones is the T1, because sometimes it's really good for you to just inverse one table. Es que en plan he visto que la parte de la data true se ha ido muy rápido, entonces he dicho, venga, voy a hacer un poquito de manipulación básica de tables y ahora ya me muevo, porque si no acabamos en una hora. ¿Vale?
Vale, no te metas mucho en esto porque si no se van a liar.
No, ya por eso, pero porque sé que les gusta un poco esto también. En plan, ya me voy a quitar a lo otro, ¿vale? okay, this was a bit to, explore the ASB table, see how it looks with that, see how can we invert it, how can we calculate maybe the sum of the column, some basic things, okay? But we're not gonna go more in detail, and now we're gonna still keep going with the workflow of the 16S amplicon, okay? So I'm gonna go back to my presentation. And so we were here, okay? We had the ASB table, we had it like that. We already saw that there were a lot of zeros. So what is the next step? The next step is what we have these ASBs, and the ASBs, when we calculate them, we just have the sequence. So we want them to assign a taxonomy. So to assign a taxonomy, as Victor explained in the lectures, one of the databases that exists out there is the Silva database. That is one of the most widely used databases. So in this database, you have stored like sequences of like a lot of microorganisms, eukaryotes, every 16S that is known. So that data to assign the taxonomy to each of your ASBs. So when you assign the taxonomy, you get a table like this. In the table, you have as rows the ASBs, and then in the columns, you have the hierarchy in the taxonomy. So they start with kingdom, phylum, class, order, family, genus, and species. So you can see that in some cases, that in the family or in the genus and in the species, you see some NAs. That's because there are some sequences that are in the database that they know the kingdom, the phylum, the class order, but they cannot go sometimes farther, and they just stop there because there is not that much any more information to assign a species, or in some cases even a genus. So if you, in your R environment, in the upright, in the variables, look for a table called taxdf, and you click it, you will open this table in your R. So let's try fast. Seguro.
So you go to the global environment, and then scroll down, and then you will find tax_df.
You click it, and then it will show up the table. Okay? Okay, just to see that you have that tables there in that in the environment. All good, all can see it. You can scroll it down, see what is there, but we are okay. So everyone good? We are gonna move to the next. Yes? In data 2. Yeah. Yeah. At the end, I will do a little overview of all these big scripts that you have. But the data 2 is complex. There is a lot of tutorials. There is also a lot of steps there performed. And yeah, I just want to show you the main steps and the main things. Okay?
You have all the scripts, yeah?
Mm-hmm.
One of the files.
Yeah, the file that you have, this amplicon.rmd, that's the whole workflow. But I'm not going to explain the whole thing, but you have it there. So in a future, with your own data, you will be able to study and apply with your own data.
So you put your input file there, and then you could run the whole pipeline just with those scripts.
Yeah, and there is a lot of documentation, but the objective is that you understand the main steps of the workflow. Okay? Okay, so we move forward. Well, this is a slide from, yes? When would you like to stop? Mejor cuando cambiemos de módulo, queda nada, una slide. Okay. So you remember this slide from Victor? So sometimes, as Victor explained, well, you are sequencing. In our case, well, you remember we have this rhizosphere, we have the spermosphere, and the bulk soil, but we're interested only in the microbes that are there. So still, when you are doing this 16S, you get a lot of reads from the chloroplast and the mitochondria. So how you filter them out? Well, you see this table, and you see this. Here is the annotation of what is a chloroplast. So, So here, for example, you see these two first ASBs. The classification is kingdom bacteria, phylum cyanobacteria, class cyanobacteria, order chloroplast. So this is a chloroplast. It looks weird because it will tell you that it's a bacteria, but this is how they have it, the classification. So then, for example, we also want to remove the mitochondria because the mitochondria is also some DNA that the reads will be there. So, for example, if you look into the ASB3 here in this table, you have bacteria, proteobacteria, alpha proteobacteria, rickettsiales, mitochondria. And this is the classification of the mitochondrial 16S in this database. So if you want to remove it, you will just need to remove these 3 rows. You just remove them. You remove them from here, from your taxonomy, and you remove them from your ASB table. And then you got rid of that problem. And then you can continue, and you won't have that problem anymore. And it's a big problem because normally the reads of chloroplast and mitochondria are really, really high. So that will bias the whole analysis and everything. So you need to get rid of them, unless you are interested in them, of course. So we see that we have the module 1, let me see, that it was this one, that the objective is to generate the ASB table. But we got 2 main outputs. One is the ASB table, and the other one is the taxonomy of each ASB. Because just knowing the ASB, what can you do? Nothing. So you need also the taxonomy. So here, I put a checkpoint. So if anyone has questions about, this is the moment, because this is the end of the first module, and now we're going to take a break, right? And then we will continue with the second and last module. So any question? Okay, good.
Go one back?
Yes.
Just 1 second.
This
Go
one?
one back.
Ah, es que era una delante esa. Sí.
So guys, so just one thing. So we have seen basically all of these steps, yeah, that are for the generation of the ASB table. That's what Guillermo have explained. So we have seen some of the points that are important, quite important. Actually, the quality check and the read filtering are the most important steps, yeah? And there are some steps that we skip because are routinary and it should be fine just running the script as it is, okay? But if they have the file, so you could potentially run all of those scripts and then see the results by yourself, okay? Because limitation of time, we cannot go through
Every
the whole
step.
pipeline, because if not, will take really long. But yeah, so if you have any question, of course, it's also, yeah. Sorry, why?
Why don't overlapping sequences during the why the quality check is going wrong? That's supposed to be about 40. And those sequences which are about 40 and doing 20.
So we need the overlapping sequence, yeah, to have a longer read, to have more information about our ASV.
Well,
because we are going to be
Here.
mapping this to a database to get the taxonomy.
So yeah.
Is that your question?
So imagine that, look at here, imagine that this is the whole 16S gene. So we have, well, the whole 16S gene, sorry, the region that we want to sequence, the B3, B4. So we have the forward primer here for the PCR and the reverse. So if we cut them too much, there will not be overlap. So then you will have two. But if they overlap, you can build the whole region. And what you want is to build the whole region. You don't want two fragments. So then you join the forward and the reverse into a longer read. That is the whole region. Okay?
Yeah, actually, that's the most important step. The So it will depend on your sequencing run. How good is the quality of your sequence? Okay? So that is what Guillermo explained.
Here.
So
So you cut them based in your quality score. Because I explained the read with the length, the quality drops. So sometimes you need to cut them to have like all high quality regions. But as I showed here, if you cut them too much, then you cannot join them because you cut them that much that the overlapping region, there is no overlap. So you need to always find a balance between quality and the length of the read.
yeah,
Total.
Yeah.
In each case, it's completely different. Don't take these 275 like as a rule. Because sometimes it and depends on the sequencer, like the reads are gonna be longer or shorter. So you need to always see with your data.
So think in this way. So you always have to do the same. Quality and trimming is always the same. So you have your length here, 330, 20 base pairs, and then here you have the quality score. You have to, with R, you have to inspect visually the quality of the read. And then you see already that it's, well, the quality that we accept for it's 30.
It's about 30.
The quality Fred score 30. So then you draw a line and then you say, okay, I'm gonna cut it about 270. And that's what you do for the forward. And for the reverse, you do the same. Yeah? So I didn't say that this green line is the quality, okay, of your read. And then, well, in the reverse is exactly the same, but usually in the reverse primer, the quality drops before. Yeah, because I don't know, it
Well,
gets more tired.
that was both of them forward. Now this.
Okay.
So this is the forward, and you can see, and as I explained, the reverse, the quality always is lower because of how the machine works and technical things. But it's most of the case. So you need to choose a point that you trim in the forward, but it's not the same in the reverse. You need to choose one for one. And in each experiment, it will be the completely different. So you need to always check in these plots and see what it works best to choose the position to cut.
If we have different framing points,
Mm-hmm.
we are dealing with the same material. At the end of our analysis, like the final product we have, will it be the same?
If you have different timings, yeah. For example, I mean, in here is what I show. Like this is the one that we apply, that is at 275. But then I say, like, what happens if we apply a more strict one? So it's 250. So the way to see it is like in this table that this software produced this table, tells you at one moment this is the track of the reads of the different steps. So if you see that at your merge step the numbers are really low, you know that you need to increase your number because you cut them too much.
I think we need to change a bit the way of doing it. Is this working? Hello, hello?
Yeah, that's true with the microphone is.
Hello, hello?
Well, they can configure it. Bueno, hacemos el break y...
Yeah. No problem. Is that working? So then what I will do then, when you have a question, I will repeat the question and then we will try to answer raising the voice. Because yeah.
Okay, yeah.
More questions.
Yes. So you mean in the taxonomy?
So you are asking for the ASBs that are not completely classified, yeah, in the ASB table. Yeah, that's good. That's an excellent question. You got all the questions? Yeah. So he's asking if we have to consider the ones that are not fully classified. My answer will be yes. Okay. So you have to consider them even if they are not fully classified because you can get some information about it. So maybe you will have some Rizobacteriaceae at family level that is unknown, it's not in the database. Yeah? So then that's why you don't get further in the classification. At phylum level is very high in the taxonomy rank.
But it happens sometimes.
It happens, yeah, I know it happens. Even higher, you get unclassified. Yeah, I don't know. If they are not in the database, it's a bit tricky. What can you say about it? Yeah. So for well, I think with 16x, it's my opinion. I would not trust that much in the ones that are at phylum level because it could be that the sequence is too short. Yeah, or maybe yeah. So I think I would not trust. I think my limit would be my personal limit would be family.
Yeah, you need to think that here you are classifying based in a sequence of maybe 500 nucleotides. So in the best case. So the DNA of bacteria is way longer. So you need to know that there could be some bias and it's not gonna work perfect.
So he's asking me if we already did the trimming. Yeah? And the answer is yes, we did the trimming, but you didn't do it in the command line. But it's the script for doing the trimming is there, where you have to introduce the numbers and it's explained. Okay?
Yes. If you follow the script and you're reading from all the script, you have descriptions of some steps and like the trimming size and everything. Then when we end the practical, we can take a look at it together.
At the end of the practical, we are going to review again the whole pipeline of data. Okay? More So Data 2 is a program that is fully running in R. That doesn't mean that you cannot run it in a Linux system. Yes. Yeah, but it's running in R.
Online or something.
Yeah,
And
but
also,
there are some steps. That's why we are not doing on site that are really are very computationally expensive. So you cannot do it with your own laptops. So that's why we pre-computed the analysis and then we gave you already the files. That's why you loaded the RMD.
Exactly.
Yeah?
All the pre-computed.
Okay.
Let's have a break.
Maybe I could add one thing. So you can try and run it with your laptops, but because it's so expensive, it will take hours. So maybe you can,
Or even days.
but
Depending on the number of samples that you have.
don't try this at home.
Don't try this at home.
No, if you have low number of samples, it will run, I think. But if you have high number of samples, and don't ask me for the minimum number of samples because I don't know. But yeah, it should work. Yeah? If you have low number of samples. Okay?
Okay, Victor, shall we give a break?
Yeah, let's have some sugar.
Okay, I think this practical will continue. You give a break now. 10-15 minutes maximum.
Diciendo nada de línea. Ya, pero porque eso luego quería abrir la 6 table y ya estaba, el plot lo tenían ahí. when we are creating the data2 table, that which one was it? Someone can tell me? Ah, the lights, that we need to put the lights off, yeah. Yes, so we were checking first we were checking and we were inspecting the reads, how they look, what type of file we get from the sequencer, then we check their quality, and then we got our ASB table and the taxonomy of our ASBs. So can someone repeat me which critical step was in the inference of the ASB table? The trimming, good. Why the trimming? Can someone tell? I don't hear anything. Good, because we need to improve the quality, so remove regions that are low quality, but still we need some overlap to get a long read. Okay, so we have that clear. So now we're gonna move to the next part of the 16 amplicon workflow. So this, as Victor showed, we're gonna here look at what can we do with this ASB table. So we can do basically a statistical analysis, and we want to see nice plots for our papers. So then our PhD go smooth, and our papers go to high impact factor journals. So we are gonna check first. We are gonna see also the alpha diversity. We are gonna see beta diversity, and we are gonna also see differential abundance analysis. So first, we're going to start with the alpha diversity. So as Victor mentioned in the lecture, alpha diversity is the intra-sample diversity. So for that first, in the R code, we create a phylosec object. So what is phylosec? Phylosec is one of these packages that probably you know that we have some issues installing some of us. And it's a really common package that is used in the analysis of amplicon data. It's an R package, and as you know from Luisa's practical from yesterday, in R we have different data structures. Like the most basic one was the data frame, that is basically a table. So normally each package has like its own data structure. So here, phylosec is not an exception. So it has a data structure that combines the ASB table that we created, the taxa table that we created, and the metadata. Remember from Victor's lecture that the metadata is really important. You need to know where that samples are coming from. So in your R code, if you open the table called metadata, so you're in your app, right, you find the variable called metadata, and you click on it, it will open a table like not exactly the same, but similar to the one that we have here, where we have the name of our samples and the location where they are. So as we say with the experimental design, we have 12 samples. We have four from the spermosphere, 4 from the rhizosphere, and 4 bulk soil samples. So everyone was able to open the table? Okay, good. So just as you know, we are combining these 3 things to do the diversity and all the statistical analysis. So now we are going to get to the alpha diversity. So then to calculate the alpha diversity, we need to apply something called rarefaction. So rarefaction, basically what it does, it corrects for sample size. So what is sample size? Sample size is the total number of reads per sample. So for example, here in the right, you can see the different samples in that in the table in the right, you can see the different samples that we have at the total reads of each of the samples. So you can see that there is high variability. There is some of them that are even like the last one, that are like almost 43,000, while some of them are in the, does it work? Okay, sorry. So like this sample, we have like around 43,000 a number of reads, total number of reads, and in other ones, like we have like the smallest one, like this one, I think, yeah, 23,000. So we need to correct for that difference in sample size. So for that, first to see the effect that rarefaction has in our data, it's normal that we plot these rarefaction curves. So in these rarefaction curves, we have in the x-axis the sample size or total number of reads per sample, and in the y-axis the number of ASBs. So basically, what we are looking for here is how rarefaction is going to affect our data. So to see that, that we can apply and rarefaction is going to be good on our data, we need to see that each line is a different sample. So we have 12 samples. So we have 12 lines. We can see that every line reaches a flat. That means that we have enough sequence depth in the sequencing that we perform to get the total number of ASBs that we could find there. Okay? So if you run in the script that you have, you go to the lines 237 to 248 and you click play in that chunk of code, it will generate these rarefaction curves. Yes?
I think this is a very important step. Can you hear me? Yes. So this is a very important step. So what this basically means is that we have reached what we call a plateau. Okay, so here we have the number of ASBs. Every time that there is a new ASB, so a new species appearing, so we will go up in the y-axis. So that means that for most of the species, when we are here, a new ASB that we sequence, we will already sequence it. Okay? So it was already in our results. So that means that we have reached the complete diversity of our environment. Do you understand that?
Yes.
Yes or no?
Yes. So how a bad sample will look?
No?
No?
No? Huh?
No, sir. If you
Yeah,
repeat
sure,
it.
sure. So here in the x-axis, we have the sample size. Okay? Sample size is the total number of reads. Here we have number of ASBs. So rarefaction curves, every time that there is a new ASB, it will be summing up here. Yeah? Every time that there is a new one. So there will be a moment in which there are more new ASBs coming up. So we have all the ASBs repeated already, right? So that's the moment that we have the plateau. So we have reached the total, the maximum diversity, yeah, in our sample. So we know all the microbes that are there. Clear now? Better?
Yeah. So if you have a sample that doesn't reach the plateau, it means that you will need more reads, more amount of reads to detect the total number of ASBs or the total diversity of that sample. So how a bad sample will look? Something like that. It just stops there. It doesn't reach the plateau. So it's telling you that maybe for that sample, you will have to increase the total number of reads to get the total ASBs or all the diversity that is in that sample. Okay, is everything understood?
No? No. Okay. So what if we have a sample that we don't reach the plateau. Yeah? So this sample that we have here in red means that when we sequence more, we get more new OTUs. So basically, we are not getting the full diversity of our sample. Yeah? So this is the case in this sample. Not like in these ones, for example, that we are reaching the plateau because we have enough sequencing depth.
How the plateau is determined?
Sorry?
How the plateau is determined?
How the plateau what?
The plateau.
The plateau is determined because when you sequence more, yeah, when you take more ASVs from your environment, yeah, those ASVs are already repeated. Then it becomes flat.
Can I add something else? So do you remember we had the table with a lot of zeros?
Yes.
But in some cells you don't have a lot of zeros. You can have 18,000. That means you found that ASB many times. So every time that a 2 evaluates one read, it's gonna match it and say, okay, this is one ASB. The next one is too different. That's a new ASB. When it's starting, that happens a lot. So you see the line going up. Because the more reads you have, the more ASBs you find. But at some point, you have so many ASBs, I think you had like 6,000. Most of the sequences you have already match something that was already identified. So you start getting more and more counts of the same ASBs. And that's why with more reads, you don't get more ASBs. And you reach the flat. Is that better?
There is another question here.
Does that mean that the sample which has high rarefaction value is more diverse than others, or
So your question is if the rarefaction curve goes higher, if that means that the diversity is higher. The answer is yes. So if you go higher in the diversity, in the number of of different OTUs, you have more diversity. Yeah.
I'm just checking here. Is it clear? Or yeah. Think about you go into a supermarket with a cart. Yeah, you load stuff in your supermarket. You go again through the supermarket and you think, oh no, that I already have in my. Yeah, and at some point your cart is basically saturated because you already took all those things that you wanted to put in there. Right?
That's a great example.
Okay.
Thank you, Josh. Thank you. Amazing. Yeah.
I think this example is a beautiful example.
Yeah.
Explaining this rarefaction. The word rarefaction, I think I just shared in your group. Maybe tonight you read it, not now. You will understand better way what this rarefaction word means. In biology, in microbiome, what Victor is explaining, what Yos has now explained with an example. I think try to understand that, right? It's a saturation of ASBs.
Yeah. That's the
That's
word,
a
I
good
think.
word,
Yeah, that's a very good word. Actually, you are saturating, yeah, of the number of ASBs, the diversity, the complete diversity of your environment. You get everything. I mean, this is ideal, eh? This is ideal.
Exactly, this idea.
This is very ideal.
So basically,
Point of ASBs.
this
Yeah, of course, you need a little more reading. Maybe tonight you would be all right. Read that. Is all okay or need some more?
Basically. Yeah, that's a good example that just said. So here you are looking for the saturation. So here you are not still applying the rarefaction. You are seeing if you can apply it or if your data is saturated. So if you see like like you have a new sample that didn't reach the plateau, so it's not saturated, the only option, one of the options that you have is you need to sequence again with more depth, so you need to saturate more that sample. You need more reads to get all the ASBs or diversity. And as someone asked before, of course, some of these samples have more diversity than these samples. Why? Just simply because they reach the saturation at a point of more ASBs. So they just have more species and diversity on them. Okay, so once you have you plot these rarefaction curves to check this is like a checkpoint of how the rarefaction and if you can apply it in your data. And then you apply that basically rarefaction will just cut it when the plateau starts. Because this, for example, here in this point, already to the right, everything is saturated. So you don't need that many reads. So you just cut it here when it reaches the plateau. And that corrects for the sample size or the total number of reads per sample. So then you need to perform this step to calculate the alpha diversity. And then once you can calculate the alpha diversity, as Victor explained in his lecture. We have different ones like Shannon and Chow. Here we have observer and Shannon, and we have it 3 blocks. Why? Because we have 3 conditions: spermosphere, rhizosphere, and bulk in our experimental design. So here we have in red bulk, we have in green rhizosphere, and in blue spermosphere. You can generate this plot if you run now the lines 237 to 248. So go in your script to that chunk of code and then just press the play button and see if you can get this plot. And please use the stick notes if some of you have problems. So 2 lines of code 237 to 248.
Did you manage? Yes?
You need, these plots need to appear. No? Okay. Go to, you go to plots. Magic. Remember, one moment please. Remember to go to the plot section in the bottom right. That's where the plot will appear. $237 to 148. No, run, just need to do the play. And just wait.
Okay, so it will take a while.
It takes some time. It takes some time. Oops, yeah. You can just press the green button. So just press it, and it will take like maybe 30 seconds or something. Yes. One moment. Yes. Error could not find function sample data. You don't have the package loaded. Do library file sec. File sec. No. Enter now. Library, so library, then brackets. And now file sec. There, and enter. Okay, you have it. And do now library, the same, but with vegan. And now vegan, like V, yeah, E, G, N, and enter. Yeah, that one you don't have to install it. So you need to install that package, okay? Anyone more? Yeah. What did it say? Yeah, just click in the.
It's not responding.
That's weird. Maybe it got stuck or something. That's weird. Yeah. Maybe it got stuck. They are.
It's coming like this. So whether this is right? Coming like this.
Yeah, and now you go to plots here. That section, plots.
Plot.
No, plot. There you go. So the plots are always generated in the plot thing. Yeah, Luisa?
Guys, it's important to find as well. Yeah. So if I think maybe this is a good moment now to bring back the overall scheme, right? When you want to go through this.
No, it's just the beta diversity and the two plots.
Okay, no, but I think explaining the CSS and so on is going to kill them.
You're going to go into a zero inflated Gaussian model.
Don't
So
go
like
there.
hide that one.
Well, or hide or unexplain and
Okay, I'm gonna say.
Although we talked about the zeros, and you gotta say something about the zeros. That
I will say that. I will say okay. CSS. Weight of height. Well,
no,
yeah, it's
I
gonna
think
confuse.
you gotta recognize towards the students that it's been super intense and complex this afternoon, and that you will skip a few things. So because how many slides are still there?
Nah, there are like 3.
But
the three heavy.
You don't want to kill them. But they don't need to do anything anymore, right?
They could, but no. Then
No.
I would just
I
not
think
do
they
anything.
have to
Okay.
run the script.
They like that, I feel that's why. I feel like them so happy when they see the plots on them. But
then keep it super simple. Yeah.
I'm just not gonna tell them to run the next plot.
Yeah,
And the
who's gonna
CS, the beta diversity, the
no other. Because if not, they will listen. I think.
Right.
But
I thought you were like.
Well,
Just I have at the end one with the alpha diversity, the beta diversity, and the bar plot, and that was just like interpretation of the results. So I'll just move fast to that one, and then like discussion a bit there, and that's all. I'm finished.
Yeah. Okay.
Okay?
Yeah, sweet and simple. They need to go home with a good feeling.
Yeah, exactly.
V3, V4 is?
Yes.
Looking at this one, the observed values, in here actually it is coming less, but how the diversity values are coming more when we are calculating Shannon?
Because the observed is just the number of ASBs.
This is number of ASV.
A number of ASBs, so it's high. Like this one has 2,000, for example. But in the Shannon is another index, so it's a weird calculation.
Number.
Yeah, you see the formula, that ugly formula.
Okay.
So it's an ugly formula that generates something. But you can see that are mostly the same.
Almost 10 to 5. Make sure you stop at 5.
Okay, we'll go first. I'm just gonna stop it. Big Luisa, just stop. We need, if not, we are gonna run out of time. Victor. Victor. Tell them to stop. Victor, we move on, if not the time. That we need to continue. Okay. Okay, I will continue. Don't worry. I mean, it's just to see the value. If not, we run out of time. We don't want to go home as late as yesterday, today. So I'm going to continue, okay? So, okay, we have the alpha diversity. So here, for example, in that chunk of code, we calculated two types of alpha diversity, number of species and the Shannon index. So, and we have our three conditions of our data set. So you can see how the bulk soil and the spermosphere had a higher diversity than the rhizosphere, and how, like, although we are using two measures, kind of the plot looks really similar. So although you use different like types of alpha diversity, most of the times the plots will look like really similar in these terms. So now we have a checkpoint here. Have questions? We'll move on. Then we go to the next one, that we have beta diversity. So the beta diversity, we use it doing CSS normalization. I'm not going to get too in deep here because of limitation of time, but what I want you to understand about the CSS normalization is that we have compositional data. So we have some ASBs with really, really high number of reads associated with them, and other ASBs with really low numbers. So then if you do the statistic analysis, it will be really biased to the ASBs that has a lot of reads with them, that are really present there. So to get rid of that problem, CSS normalization reduce the weight of the highly abundant ASBs and increase the weight of the really low abundant ASBs. That's the key point. So for that we use this metagenome sec-R object. So it's another data structure with that is the metagenome package. And then this is the formula. We are not going to get too in deep, but if you want to know more about the normalization, you can check Joseph Paulson papers that where he made all these package because out of this CSS normalization. So once we have, so then for alpha diversity, remember that we rarefy the data. So for beta diversity, we use CSS normalization. You don't apply CSS normalization in the rarefied data. So rarefied for alpha diversity and CSS normalization for beta diversity. So how we calculate the beta diversity? Here we have the principal coordinate analysis. We already discussed it a bit in Victor's lecture, what it means. So we have two axes that explain the variance between samples, and each dot is one sample. So we can see that the first axis is playing like around 35% of variance, and the second, the y-axis, is playing around 7.8. So that means that this axis is more important than this axis in explaining the variance. And we can see, similar, like in the alpha diversity, how the rhizosphere is kind of here alone, and the spermosphere and the bulk soil are kind of together. What it tells you this? This tells you that the bulk soil and the spermosphere microbiome is really similar, while the rhizosphere is more specialized. So sometimes you have these plots, and you can plot this in your paper and say like, oh, look, this is what I just said. This one is different to this one. But always in a paper, you need to support your assumptions with some statistics. So which statistics you can apply here? Basically, a permanova. A permanova just tells you if there is a difference, you just test the hypothesis that if there is a difference between groups. That's all. So in this case, we performed the permanova in R and got a p-value of less than 0.001, what is quite significant. So then we see that in the beta diversity, this. So anyone questions on the beta diversity? Okay. So now, as Josh showed in his lecture, a lot of papers, they show this bar plot at the phylum level, where we have the abundance and the samples that we have. And this is nice, but it's really general at the phylum level. So if we have this high resolution of ASBs, why would we want to see difference at that high level as is phylum? For some research, it's nice, because, for example, you have two samples that are really different, you will be seeing difference at the phylum level. But yeah, for our case, we just want to pinpoint a specific species or taxa. So this is not that interesting, but it's a figure that you will see in most of the papers, and that doesn't mean that it's useless. So now we move to the last point, that is the differential abundance. So here is where we want to pinpoint a specific ASBs. So pinpoint a specific strain, species, taxa units, that are more abundant in one one condition or in another condition. So here in this nice overview slide, we will be in this section checking the differential abundance at the taxonomy level, not the function, the taxonomy. Why? Because we are doing 16S amplicon. Function will be with metagenomics data, shotgun metagenomics. So for the differential abundance, we need to perform some statistics. So inside of this package, metagenome-seq, they applied this model that could sound really scary, but it's called like zero-inflated Gaussian model. But this is just two terms. One is Gaussian mixture models, that is just see like it like applies some Gaussian distribution, like normal distributions in the data, and zero-inflated, it means that it's adapted to a large number of zeros in our data. That's what we saw in the ASB table, that we had a lot of zeros. So this model takes that into account so we can perform statistics. So then we can perform a contrast. For example, in our case, we perform the contrast spermosphere versus rhizosphere, and then you will get log-fold chains, p-values, and adjusted p-values of each ASB. Then what normally you do, you filter this table. So you can filter in different ways, but normally what people do is you filter for a log-fold change of more than one, normally one, between 1 and 2, and a p-adjusted value of less than 0.05. So that will be your significant ASBs. In the contrast, spermosphere versus rhizosphere. So then, this table is your main result. Now, how we visualize this table? There's different ways. Wait, that should appear the first, by mistake. So we can visualize with volcano plots. What's a volcano plot? A volcano plot, we have two. In the x-axis, the log fold change. And in the y-axis, we have the minus log 10 p-value. So what you can see here is, because the contrast that we did is a rhizosphere versus a spermosphere, what is in the right is ASBs that are up in the rhizosphere. While what we have here in the left, in red, is the ASBs, so each point is one ASB, ASBs that are up in the spermosphere. And the ones that are gray are the ones that are non-significant when we apply that filter of more than log fold change this and less than a p-value of 0.05. So this is a common way, and this plot you will also see it in transcriptomics and in other type of analysis. Then, to also check more information of these significant upregulated in spermosphere or in rhizosphere, you can perform bar plots. And you can organize them by phylum. So here, for example, you have in the x-axis the ASBs, and they are grouped by phylum. You cannot see all the names because there's a lot, but for example, here you have acidobacteria, here you have protobacteria, and here, for example, you have chloroflexi. And in the y-axis, you have the log fold change. So if the log fold change is positive, it means that it's up in the rhizosphere, because we did contrast rhizosphere versus spermosphere. And in the log fold change is negative, it means that it's up in the spermosphere. So this is a nice way to see like the taxonomy, general taxonomy of your ASBs that are differentially abundant between rhizosphere and spermosphere. So now I want to do a checkpoint here if you understand, but then I would like to also maybe move here and try to interpret these three plots. So we did a comparison, spermosphere versus rhizosphere. So we got the alpha diversity, and we saw that the spermosphere and the bulk are really similar, and the rhizosphere has a really lower, more lower diversity, right? Here we can see the same. The blue points, this cloud of blue points, is smaller, that is up in rhizosphere, is smaller than the cloud, the red cloud of points that is up in a spermosphere. So both of them are telling us the same. And here in the bar plot, you can see more bars going down than more bars going up. So one of our main conclusions of this analysis will be that the spermosphere is more diverse and have more ASB differentially abundant than the rhizosphere. And well, and this will be the interpretation, so you can see how all plots kind of match together to get to the same answer. And yeah, so this is all. And well, you have all the code available in that markdown. Now we don't have time to go maybe through it, but if you have any questions or if you want to adapt it maybe for any project of you, please come by to me and I will explain you more in detail, but you have a lot of description inside the plot also. Okay, thank you so much. And well, if there's any question about everything.
Yeah, I think it's very important to remark that you have the code. Sorry.
Yeah, go here.
I think it's very important to remark that you have the code, yeah, and then you could easily run your own data with these scripts. And there is a description of every step, not only to perform the statistical analysis, but also to perform the data to pipeline. Okay, so you could take the raw script and then put it, set the directory in R on your folder with your data, run it, and it should potentially work, right?
Yeah, but be careful with running it in your own laptop and maybe explodes.
Yeah.
So you will need a server preferably.
Yeah, that's very important. Yeah. So Data 2 is well, it's quite demanding program. So and it's computationally expensive. So yeah, you will need yeah, most likely a server to run some of the steps. Yeah. Okay. Yeah. I think with that we will close today. If there are no more questions. Okay, maybe another 5 minutes. Anybody has before we discuss it?
Raise your hand and whatever may be the question. Yeah, there is a question from this side. Yeah.
So, when we were doing the Shannon graph for alpha diversity, two graphs were there. One representing the observed one, and the other one was the Shannon. Can you tell what is the difference between these two lines? Because bars were quite different from each other.
Yeah.
Can you compare different types?
Yeah. Well, no, I think it's okay. So.
Okay, so the question was that what was the difference in the graph between Shannon and observed OTUs. So in this case, there was not a big difference, or at least was not significant difference. What was different was within the treatments. So what we could see is that the bulk soil, yeah, was as diverse as the spermosphere, meaning that there was little selection in the spermosphere phase, and in the rhizosphere we have lower diversity. Okay, and yeah, so in Shannon and observed OTUs we saw the same trend. So that means that yeah, both yeah, diversity indexes were similar. Okay.
We can use that for shotgun sequencing also.
Yeah, whether the data sets was also for metagenome reads.
Shotgun.
We can use data too for metagenome. Yeah. It's only for amplicon sequencing, or it's also for metagenome.
No, so the question was if we can use data too also for shotgun metagenomics. No. So for shotgun metagenomics there are other programs because you have to think that the nature of the data is completely different. So with 16S amplicon we are amplifying a fragment that it's always the same size, everything is the same. When we are doing shotgun metagenomics, yeah, you are amplifying everything that is in that particular environment in that sample. So you need to follow other methods, but the quality trimming is the same. Okay, so the quality, I think we will show maybe something in the next practicals. We'll see if we have time. But yeah, you will follow other tutorials, other programs, like for example FastQC. Yeah. But I will show in the metagenomics lecture, I will show the overview of the programs that you can use for metagenomic analysis, for shotgun metagenomics.
Okay. We will call it a day. Very good.
Okay, so this is a summary for well, for everybody, but especially for the ones that are attending online. So they are online participants. So what we have learned today, or what we have done today during the lectures and during the practicals, so we have learned what are the different tools for metagenomic analysis, for microbiome analysis, and well, we know also how to decide which tool we have to use. We also have reviewed the different methods for amplicon sequencing analysis, and to name them, basically it's 16S, 18S, and ITS amplicon sequencing. We know what is the difference between OTUs and ASVs and how we produce them. We have learned about also the difference between alpha and beta diversity, and then we also know how to do microbiome data analysis. We have learned some of the most important concepts, and well, what is more important, I think, is that we also have learned how to go deep into the differential abundance between our treatments, and also visualizing our results. And in the afternoon, we have go through an R script that contains not only the visualization tools and the differential abundance, but also the data2 pipeline for processing sequencing data derived from amplicon sequencing. Yeah, and with this, I think we stop for today. No? Thank you very much all for being there and for listening.